weight of t prime is less than the weight of t, then both trees should differ by at least one edge. So let's assume the trees to be like this, where they differ by an edge like this. There's an edge E here, not here, and there's an edge E prime that is not here. So what we are going to do is, we are going to put that edge E here in this T prime. So we are going to put that edge E here, the tree T prime. Now, if that is the case, we just proved what? And we, by assumption, what is the minimum spanning tree? Our T prime was a minimum spanning tree, right? Isn't it? And what we just proved, if you put an edge that was not part of a minimum spanning tree on a minimum spanning tree like this, that edge is going to be the largest weight edge in a cycle. Isn't it? We just proved that. So which means, and of course, if you put this edge and you're creating a cycle, there should be at least one edge in the cycle that should not be in this tree T. Because if all the edges of the cycle are in this tree, then this tree is going to have cycle. Right? All these four edges, if 1, 2, 3, if all these four edges are in this tree, right, they're going to have cycle, isn't it? If all the four are here, this is going to have cycle. So there should be at least one edge that is in this tree T prime and not here. Right? There should be at least one edge basically in the cycle actually that is not in this tree. Because if all those edges in this cycle are in this tree, you're going to have a cycle here. And this is not a cycle, this is a tree. Right? So there should be at least one edge, which is say this E prime, that is part of the cycle and not in this tree. Right? So again, going back to what I said, if this was a minimum spanning tree, the weight of E has to be what? Greater than the weight of E prime. Right? Because what we just proved, if you put some edge that was not virtually part of a minimum spanning tree, that edge is going to be the largest weight edge among the edges that are in the cycle. Now we have to argue if this is possible. Now you see that E prime basically connects these two vertices, right? Now this is part of one cut and this is part of another cut. So we know that Kruskal's algorithm picked up edges in what order? In increasing order of edge weights, right? So if our Kruskal's algorithm gave us this tree where E prime was not there, because E prime is here and not here, that's our assumption, right? And E is there, which means the weight of E has to be less than the weight of E prime. Because Kruskal's algorithm considered edges in increasing order of edge weights. So it preferred to choose E over E prime only because the weight of E was less than the weight of E prime. Otherwise, if it was the other way around, E prime would have been there and E would not have been there. And the fact that E was connecting the two cuts rather than E prime means the weight of E was strictly less than the weight of E prime. Is that clear? So, which means this is not possible. Okay? If that was not possible, what could be possible now? We could remove E prime from the cycle and make E to be part of this tree. And by doing that, we can only further reduce this because we have established the weight of E is less than the weight of E prime. So we can transform this tree T prime by removing this edge E prime and adding edge E. And that's going to create some other tree T double prime, and the weight of this T double prime is going to be only less than the weight of the T prime. But what was our assumption? This is a minimum spanning tree. Right? So it's a contradiction again. And also you can see here, by doing this replacement, what we are doing, initially the two trees differed by an edge, right? There was an edge here that was not here and vice versa. So now we have reduced the edge difference by 1. So now we have made this edge E that was here also to be part of this tree. So we are making them, this T prime to become structurally more closer to this tree T. And by doing that, we are only reducing the weight if possible, we are not increasing the weight. Is that clear? So we will get a new tree T double prime by doing this transformation, and we can repeat this process by trying to make this tree become structurally closer to this and eventually same as this. And by doing that in each transformation, we are only reducing this further and further. And eventually the weight of this tree is going to become what? When they become structurally the same, this is going to be the weight of T. Right? So we are going to only make it converge to this tree T. And each time we are only reducing the weight if possible. Okay? So let me repeat the whole thing again. Okay, so how we prove the Kruskal's algorithm. So let's say this tree T is what is found by Kruskal's algorithm, and you know how it works. You pick edges in increasing order of edge weights, right? And want to prove that there is a minimum spanning tree. To prove that there is a minimum spanning tree, we assume the contradiction that there is something else of T prime that's lower in weight, which means weight of T prime is less than the weight of T. That's our assumption to start with. And we want to discuss or argue whether that is possible or not. So the way we are going to do that is, if the two trees have to be of different weights, they have to be structurally different. If they are structurally the same, what will be the case? They will be having what? Huh? The same weight. So if structurally same means they have the same edges, then they should have the same weight. So let's say this is our tree T prime, this is our TT, found using Kruskals. So when they have to be structurally different, there should be some edge difference. Edge difference means there should be one edge here that is not here, and some other edge here that is not here. So here they are differing by one edge, means there is an edge here which is not here, and here which is not here. The other four edges are there, right? So let's say this edge is E prime, and this edge is E. So what we are doing is, we are taking that edge E, which was our Kruskal's spanning tree, and putting that here, which we assume to be the minimum spanning tree to start with. Right? So what we proved in the previous theorem, if I put an edge on a minimum spanning tree, that's going to create a cycle, and that edge is going to be the largest weight edge in that cycle. And based on that, I can say the weight of E is greater than all the edges that are part of the cycle. Right? And notice that all these edges, in this case all these four edges, cannot be in this tree T. Because if all these four edges are here, like this is a cycle. And we know that this is a tree, not a cycle. So which means there should be at least one edge, like this E prime, which is part of this cycle now here. And this E prime is virtually T prime, because you only added E to be part of the cycle. So rest of the edges are already in this tree. So there should be some edge like this E prime that is not part of this tree. Right? So, but since this, by our previous theorem, this is going to be the largest weight edge among the edges in this cycle. So we can say the weight of E is going to be the weight of the E prime, according to this. Now look at this. If that was the case, what it means, this edge E prime is like this, and the way Kruskal's algorithm works, it picks edges in increasing order of edge weights. So this is one component and this is another component, and Kruskal's pick E over E prime because only the weight of E was less than the weight of E prime. If weight of E prime, let's say this is some 10 and this is say 30, if this was the case, we would have picked this edge to connect the two cuts rather than this edge. The reason why we picked this is because this is of lower weight than this. That's why we picked E over E prime. So the way Kruskal's algorithm works, it is very clear that the weight of E has to be less than the weight of E prime. Which means what we had before cannot be true. Right? Because this is the other way. Weight of E is greater than the weight of E prime. So this is not possible. Which means what we can do, we can optimize this tree T prime further by, since weight of E is less than weight of E prime, we can remove E prime from the cycle and retain E to be part of this thing and make it still a connected tree. And by doing that, what we are doing, we are trying to reduce this weight of E prime even further, because this is going to be, I'll say 10 and 3, from whatever it was, T prime, we're removing E prime and adding E to it. And that's going to create this new tree P double prime that's going to be of weight less than the weight of T prime, because we're only reducing the weight. And by doing this transformation, what we are doing, we are making this tree to become more structurally closer to a Kruskal's tree, because now we have the same edge E also part of this tree. So they are becoming closer to this tree, and by doing that we are only reducing the weight. So if there was another edge difference between these two, we can go through the same process and make this to have one more edge that is this tree, right? So we can make it become structurally closer to Kruskal's tree, and each step will only reduce the weight of the spanning tree, cannot increase it. So eventually the two trees will be the same, and which means the weight of the spanning tree is going to only what? Approach or converge to the weight of what the Kruskal's tree has. So it's going to reduce further and further and become same as this, which means this is whatever the tree T prime, T double prime, whatever the transformation you do, all those things. If this was a minimum spanning tree to start with, we can even reduce and reduce further, and it's going to only converge to our Kruskal's tree T. So which means these are not minimum spanning trees, because we cannot reduce a minimum spanning tree's weight, first of all, right? So if we can reduce means, again that's not possible, but eventually it's going to converge. So which means this is going to be smaller, right? All these things have to be larger, because by doing the transformations we are only reducing the edge weights. Okay? So that's how we prove the correctness of Kruskal. Okay, so we have two more, one small thing, and this we already discussed it. There's two more theorems. This is like if you have the graph with all the theorem basically is you could have more than one minimum spanning tree for a graph, as long as the graph does not have unique edge weights. Unique edge weights means like you have more than one edge and the same weight. Here there are two edges having weight 1 and two edges having weight 2. Right? Unique edge weights means it's something like 1, 2, 3, 4. If you have graphs with unique edge weights, that's the other theorem, then there can be only one minimum spanning tree for that graph, which we'll prove next time. But what this theorem states is, if the graph does not have unique edge weights, so something like this, then you can have more than one minimum spanning tree. So for example, if I run Kruskals on a small graph, I would pick this, and you can pick one of the twos, right? So this is one minimum spanning tree, the other minimum spanning tree could be something like this. So both add up to 4. And structurally definitely they are different because they have different edges. Right? So that is one thing, little thing you have to know. And just one more minute. So we'll just look at this. A maximum spanning tree is very similar to a minimum spanning tree. The only difference is the sum of all the edge weights is maximum rather than minimum. So how to find a maximum spanning tree? Do the same process. Instead of picking the edges in the increasing order of edge weights, pick them in the decreasing order of edge weights. Okay, so if you run on the same graph, you pick the largest edge weight. In this case it is 15. So 15 again check, they are the same or different component, they should be in a different component, so you bring them together. Then the largest edge weight is going to be 11, so they are a different component, so you can bring them together. And then the largest edge weight is 9, they are again a different component. Then what else? You have several 8 out there, right? So again, there's also a 9 there. So pick up that 9, that's going to bring these two together. Okay? And then you can pick this 8, that's going to bring these two together. And then you can pick up this 7. So you pick edges in the decreasing order, which means you pick the largest edge weight first, and then the next largest, and so on. And what you get is a maximum spanning tree. Again, the definition is the sum of all the edge weights is maximum rather than minimum. So the same method, just instead of picking the edges in the increasing order of edge weights, pick the largest one first and then the next largest and so on. Okay? So by that you can find what is called the maximum spanning tree on a graph. Okay? So we'll stop here.